Okay, so we might as well carry on with our very intense discussion about limits. So if you recall from last time, we had just about gotten ready to start a special case. And, up to this point, all the limits we've been doing have been very straightforward. They basically are all polynomials, and direct substitution into x will usually give us the answer that we're looking for. Like here, for example, we directly plug 0 in, or we could solve this by directly plugging in 0 for all these x's and coming up with the correct solution. The other option is to use the rules to break it up into individual pieces, but even then, for the most part, except for the constants, what we're doing is we're solving by substituting 0 in for x. Now we're going to move into some more complicated cases. And so what happens if we do end up getting division by 0 as a result of direct substitution? Well, you might think, well, that's it. We're done. We can't do anything about it. But that's actually not true in every case. Now, here's an interesting result from calculus. If we have two functions that have the same limit, the same value for all x's except possibly at one point A, then we can prove, although we're not going to do that here, that the limits are the same. Okay, so what exactly does that mean? All right, well, let's see. Let's start with an example of this. So here we want to find the limit as x approaches 1 of x squared minus 1 over x minus 1. Now, you can see that if we directly substitute 1 in for x here, we're going to have a problem. And by the way, here's the graph. You can see there's a hole where x equals 1 because that's where we have division by 0. Okay. On the other hand, as we've already seen, as we approach x from the left, as x approaches 1 from the left, function approaches 2. And as x approaches 1 from the right, the function approaches 2. So it means that, as we've seen in a previous example, the limit here, as x approaches 1 of f of x is just 2. But here's what this result is actually telling us. We know that x squared minus 1 over x minus 1 can be reduced because x squared minus 1 actually equals x plus 1 times x minus 1. And you can figure this out with traditional factoring, but you'll see that if you apply FOIL to these two terms, you'll end up with x squared minus 1. So what you've actually got here, as you can see here, is x plus 1 times x minus 1 over x minus 1. So what the theorem is basically telling us here is this. This is the original function. It has a hole. This function does not have a hole in it. Okay, so you've got let's draw these side by side. And then this would be f of x equals x plus 1. So basically, what this result is telling us is that the two functions are identical to each other except when x equals 1. Here, we have a hole in the function, which means the function is undefined there. And here, when x equals 1, the function just equals 2. So what that implies is that because the functions are identical everywhere else, that implies in turn that the limit, actually, let me write this on the next slide. So I'll just write this as x squared minus 1 over x minus 1, since they are identical, except when x equals 1. Now, of course, if that's the case, that means the one on the right and the left are the same. So we solve for the one on the right because it's the simpler one. And that means we can just use direct substitution and we end up with 2. So what's happening here is we are actually taking the limit in a slightly different way. Here, we're able to demonstrate that because um, the function has the same value when x approaches 1 from the left and the right, that implies a limit of 2. Here, what we're saying is that we have another function that is identical everywhere except at that point. And since its limit is 2, then the limit of the original function must also be 2. So it's basically another way of justifying this result. Now, sometimes this will be helpful. If you can take a function and reduce it to something simpler, except possibly at one single point, then you can go ahead and do that, and it might make it easier to solve for your limit. Okay. Now, this is the one we're going to need a lot. The indeterminate form 0 over 0. It's as if it weren't bad enough with this last one that we had division by 0. Here, it's even worse because we have 0 over 0. And so you might again say, well, when this happens, we might have to give up. There's no way we can get a limit. Well, that's actually not necessarily true. So it turns out there are several forms that we call indeterminate, and we'll run across several of them as we go through the course. But this is one of the ones where we see very frequently. And so 0 over 0 has its own unique way of being solved for. What exactly are we going to do? Now, like here, notice this one. Since these are both polynomials in the numerator and the denominator, based on what we've been doing up to this point, you might think, well, why don't we just plug in 3 and see what happens? Unfortunately, though, you can see here, when we do that, we get not only division by 0, but 0 is also in the numerator. So now, by the way, there's usually more than one way of dealing with these indeterminate forms. It's just that some of those ways require us to learn new material from, let's say, chapter 2 or some of the later chapters. So this is not the only approach to solving for this 0 over 0 indeterminate form. But it is a way. It does work. So what we're doing here is we're factoring. And we're eliminating these 2. And now, by the way, this is based on the principle we just saw, that because these 2 functions are going to be the same except for x equals 3, that implies that they'll have the same limit, whatever that is. So basically, what you're being given the opportunity to do is solve the simpler of the 2. Yeah. Now, what I'd like to do, we might as well go back to Symbol Lab and show the difference between the 2. So on the one on the left, of course, there'll be a hole in the function at x equals 3, as we've seen. The one on the right will not have a hole. Okay. But let's just prove it. Let's go to Symbol Lab and prove it. All right. So again, now that, oh my God, look how complicated this one is. Y equals x squared minus 3x over 2x squared minus 5x minus 3. All right, let's take a look at this graph. And again, we've certainly know it's not a linear function, but we do know that we should expect to find a hole somewhere in here. Oh, it's not even on here. Hold on. There it is. There it is. It's right there. Sorry. I didn't even see it. Here's the hole, right? My pen seems to have rolled away. Ah, here we go. Okay. So yes, I just wanted you to see right here. Here's the hole. So when x equals 3, the function is undefined. Okay. And that's exactly what we would have expected. But when we replace this with the version that does not have a hole, because we've reduced it, that would be this x over 2x plus 1. Now, and unfortunately, we can't show them side by side, but you'll recognize from the graph x over 2x plus 1. The only way they're different is that the hole is missing. Let's see, it would have been right here. Yes, so in other words, at 3, when x equals 3, somewhere along here, here it is. There's no hole there. Otherwise, these are the exact same function. So therefore, the limit of what you're seeing here is the same as the limit of the original function. And of course, now we can solve that very simply by simply plugging in x equals 3. Okay. And we end up with 3/7. Now, of course, this is a great strategy as if it is possible to reduce the numerator and the denominator. In other words, if they have a common factor. If they don't, well, then we have to try something different. Like I said, for any given indeterminate form, there can be multiple ways of getting to the solution. Okay. Here, it just so happens that we were able to factor out a common factor from the numerator and the denominator, which was x minus 3, and that made things a lot simpler for us. Oh my God, what about this one? Now you can see what the problem is. As x approaches -1, we're going to have division by 0 here. Guess what? We'll have the same problem in the numerator. Oh, hold on. So if you plug this directly in, you'll have radical 1 minus 1 over 0. Here we go, 0 over 0. Now you can see there's no common factors there. So what are we supposed to do? Well, there's a very clever strategy for a case like this. What we're going to do is introduce the concept of the conjugate. What does that mean? Now, by the way, you may remember having seen this in pre-calc. Let me just quickly remind you. If you recall, when you were dealing with complex numbers in pre-calc, that would be any number that takes the form a plus bi, where I, of course, is the imaginary number square root of -1. This term and this one, where they're only different by the sign in the middle, are said to be complex conjugates. Now here we're not dealing with complex numbers, but the concept is the same, because if you notice, what we have here is radical x plus 2 minus 1 and radical x plus 2 plus 1. So because the sign is different, only the sign is different here, these are said to be conjugates of each other. Not complex conjugates, of course, but conjugates. So here's what we're going to do. We're going to take this original messy limit, which leads to 0 over 0, and then we're going to multiply by this expression, which clearly is equal to 1, which means we can certainly justify doing this. But what we're doing is actually creating a ratio which is equal to the conjugate of the numerator here over itself. Okay, now you're probably wondering, why are we doing this? Well, you'll see there's a very good chance that this will help reduce the problem so that it's no longer going to give us 0 over 0. Okay, so let's see how that works. Now, we can multiply together. Let me just do this on the next slide. What happens when you multiply radical x plus 2 minus 1 times radical x plus 2 minus 1, plus 1. So why don't we try FOIL? Everybody remembers FOIL. First, now when you multiply these two together, you're going to wind up with x plus 2. Okay, the outer is here. The inner is here. And then last is here. Oh, whoops. Now, here's a great thing about conjugates. When you multiply them together, the outer and inner terms will always cancel each other out. That's the purpose of doing this, so that what you're left with is x plus 2 minus 1, which is simply x plus 1. So that becomes our numerator. What about the denominator? Okay, well, this one, well, we can't use FOIL on this one, but we can multiply them anyway. So we're going to have x plus 1. Well, actually, no, my mistake. We can use FOIL here because we still have two terms in each set of parentheses. We have two binomial terms. So let's do it. F. Now, it gets a little messy here. We're not going to have any cancellations, unfortunately. So we're going to have x times radical x plus 2 here. O is x. I is radical x plus 2. And then last is these two, which is just 1. So we've actually got two terms here that can be combined. And so you can see what you actually could do here is rewrite this as x plus 1, radical x plus 2, plus x plus 1. Okay, well, it's a bit of a mess, but it's certainly, it may avoid the problem of 0 over 0. So yeah, you can see I don't have any room here for that. So here's what we'll do. We'll write it down here. Okay, so in the denominator we had x plus 1, radical x plus 2, plus x plus 1. Okay, exactly like we have here. Okay. Now, here's the beauty of this. You might say, well, it looks like we still have a mess on our hands, but now all of a sudden, look what happens. We can reduce this. So that was the whole point of doing this. So we can reduce it to something that does not give us 0/0. And now when we plug in that -1, we're just going to wind up with um, 1 over radical 1 plus 1, which is just a half. Wow. Now that was complicated. Who would have thought to use conjugates here? Well, after you get enough practice, you'll see that there are certain things, certain patterns that repeat themselves. And by the way, I think Symbol Lab can do this too. It does have the capability of doing limits if you want to double check your results. But you do need to learn these simplification rules. So anyway, what about this one? Well, once again, if you notice, if you plug in 1 directly, what do you get? Yeah, 0/0. What do we do with this one? Well, one thing you probably should do is, at the very least, combine the fractions in the numerator just to see what happens. All right, let's do this right now and see what happens. So what we're trying to do is combine these two terms. So we need a common denominator. So we'll multiply the first term by 2/2. The second term will multiply it by x plus 1 over x plus 1. So what do we have? Okay, so I've consolidated the two, and I end up ultimately with 1 minus x over 2x plus 1. Now that's the numerator. Oh, so you maybe can see where this is going. Um, so that means that our numerator, like I said, is 1 minus x over 2x plus 1. In the denominator, we still have x minus 1. So so we're getting close to being able to simplify this. Now, there's just one problem. The numerator way up here, we have x 1 minus x. Here down here, we have x minus 1. What we could do is rewrite this as let's see. I'm not sure, actually, that may not help us anyway. So basically, don't forget, when you have an incredibly messy function like this, remember that this is equal to this. What you're basically doing is dividing by a ratio is the same as multiplying by its inverse. So if I rewrite this with a 1 down here, you can see that I have negative x minus 1 over 2x plus 1 times 1 over x minus 1. Now we're getting somewhere. These drop out, and I have negative 1 over 2x plus 1. And remember, I'm trying to take the limit as x goes to 1. So if I plug in 1 here, I'll end up with negative 1 over 2, 1 plus 1, or negative 1/4. Yes. Okay. So of course that was already in the slides. I just wanted to show you how we got that. So it was a bit of a mess, but we did it. Okay. So really it was just a lot of algebra. But yeah, this thing up here, this ratio, this little this comes in handy quite often. So it's just a question of taking this ratio of ratios and then saying, well, listen, why don't we just rewrite it as the numerator times the inverse of the denominator? It's just so much easier than trying to figure out what cancels out what. Okay. And if you notice, I added this little 1 down here just to make it even clearer exactly what we're doing. So, all right, so that one, we were able to get around the problem of 0 over 0 by a lot of algebra. Now, this one, you can see it's going to be very similar, okay? Because here, what do I have? With direct substitution, I'm going to have 1 over negative 3 plus 2 plus 1. So this is 1 over negative 1. And that's just 0 over 0. Okay. So once again, we'll follow the same steps. Why don't we combine the two terms in the numerator? Okay. And so the numerator, 1 over x plus 1 plus 1. This will be easy because we can just rewrite 1 as x plus 2 over x plus 2. So we end up ultimately right here. Okay, so this is where we started. The 1 is the same thing as x plus 2 over x plus 2. And so that leaves us with 1 plus x plus 2 over x plus 2, or just plain x plus 3 over x plus 2. So you can see then we plug that into the original equation, and guess what happens? I'll put a 1 here, which will not affect the value, and rewrite it by multiplying by the inverse of the denominator. And I'm left with, very simply, with 1 over x plus 2. And now substitution does not lead to 0 over 0. In fact, it leads us to negative 1. Okay. So what starts to happen is after you do enough of these, you start to look at it and say, well, you know what, I think I can see what I should be doing here. So the first thing you always do, of course, is find out if direct substitution leads to 0 over 0. If it does, you've got a few options. For example, here we just we factored. Okay, in this first case, we factored out. We had a common factor in the numerator and the denominator, so we got kind of lucky. And so then you can solve for it directly. Here we used conjugates, and that helped a lot. Then we had, and then these next two, we combined the two fractions in the numerator so that ultimately made it possible to simplify this and solve directly. Okay. What about this one? Well, again, you can see if I plug in zero for these x's, I'm going to wind up with zero. Um, oh, um, hold on a second. Let's just confirm this. It's not immediately obvious. Let's try this. We need a common denominator. Oh, actually, I still don't have enough room. Hold on a second. I'll put this up here. How about that? To the second term, we don't have to do anything with it. Okay, so that means we have and when we consolidate these into one term, we have x over x minus 5. And now direct substitution does give us 0 over 0. So that means, we have to look for a strategy. What can we do now? Okay, you can see it here. So this is what we were able to do. But guess what? While direct substitution leads to 0 over 0, these cancel out. So that's why this is what we're trying to accomplish. It's true that even when we get to this point, direct substitution leads us to 0 over 0, but this also meant we could cancel out the two x's. So in other words, the original function would have had a hole at x equals 0. This function here, 1 over x minus 5, does not. Okay. So therefore, we know that they have the same limit when x equals 0, and that limit is negative 1/5. Okay, now there's a very theoretical result here called the squeeze theorem. I just want to briefly mention it. What it basically tells us is that if you have three functions such that g of x here is always in between f of x and g of x, h of x rather. For example, I'll try make something up right now. Oh, wait, sorry. The h of x is the one that goes on the outside. This is supposed to be g of x. So what this is supposed to show us is that these functions, g of x is always in between the other two. So how does that help us? Oh, here's a good example of this. So what they're basically telling us is that there's going to be some point where they all have the same limit. So there's what this is implying is that the limit as x goes to a of f of x. So now how does that help? Well, now basically they're introducing this here to show us how this can make things easier for us when we try to calculate limits of trig functions. I mentioned this before, that we will at some point need to be able to calculate limits for trig functions. So here, direct substitution will give me, and by the way, if you, like I mentioned this in one of the earlier sessions, that on your calculator, you have the TI-84, for example, you can just solve for this directly. Cosine 0 is actually equal to 1. So basically what they're showing you here in this diagram is, imagine that the three functions, the g of x that we just saw, here's our f of x, and here's our h of x. And it basically is showing that in this particular case, the point where the three have the same limit is 0. Okay. So the squeeze theorem just basically guarantees that this point exists. And sometimes this can come in handy. If we already know the limits of the other two functions, we can figure out the one in the middle just by applying this theorem. I don't know how, I mean, it's a very theoretical result. So, but it's one of those things where we keep in the back of our minds that if we're really desperate for a solution, then we might need to turn to something like this. Now, the book goes out of their way to identify, they're giving us these two formulas without proving them, and only because they may come in handy at some point. We'll get back to this later on, but they want to make sure you're aware that these two limits, for example, the limit as x goes to 0 of sine x over x is 1, and then this limit as x goes to 0 of 1 minus cosine x over x is 0. Now, they're not trying to prove it, not just yet at least. What's interesting is that this one actually leads us to 0 over 0. So that means there's something is going on behind the scenes that was used to reduce this so that it could be solved for with 1, although they're not showing it to us just yet. And then here, it's the same thing because the cosine of 0 is 1, as we just saw. But if you use the right trig functions, you can simplify this and end up solving by reducing. So what this tells us then, like let's say, for example, you have the limit as x goes to 0 of tangent x over x. Direct substitution would leave you with 0 over 0. But if you recall from our review, the tangent of x equals the sine of x over the cosine of x. Well, how does that help us? Because what I'm going to do here is rewrite this tangent as sine x over cosine x, and then algebraically that's equivalent to what you're seeing here. And now, remember, as x goes to 0, this term, as we just saw, they gave this to us, has a limit of 1. Now the cosine, if you recall, this one will solve with direct substitution. So 1 times 1 over 1, which is just 1. So here we're taking advantage of trig identities to solve for this, but that's, given that we have this identity in our back pocket, And there's a lot of them. We can look up in a chart. There's a whole slew of these, but knowing these two basic ones can help us solve a lot of different trig limits because as we saw um, in our previous lectures, all the other trig functions are ultimately based on sine and cosine. So anyway, so now we're ready for the third part of this discussion, which is called 1C. Now here we're going to start by revisiting the idea of one-sided limits. Now here, of course, this is a two-sided limit. And you can see the domain of this function is 3 up to infinity, including the 3. Now, this, by the way, this is an interesting case. Pretty much all the functions we saw earlier, either they were defined over the entire real number line, or else maybe there was a single hole in the function. Here, we have to restrict ourselves to the domain of 3 up to infinity, because this is what the function looks like. So we try to take the limit as x goes to -3. -3 is not part of the domain. That means, in other words, we're trying to find its limit right here. And well, it doesn't exist, does it? It can't. So this is another way in which a limit may not exist. Okay, remember before we saw that a limit doesn't exist if the limit from the left and the right are different from each other. Another way that a limit may not exist is if we're trying to approach a point that is not even part of its domain. So x coming up to -3, well, that's not getting us anywhere because this is not even part of the domain. So this tells me right away that this limit is undefined. Okay. Now, I think that something I see there's a typo here. This should have said 3 plus, and so should this one. So basically, what they're telling us here is that because the domain is everything from 3 up to infinity, we can evaluate the right side limit, or one-sided limit here of as x goes to 3, because that is part of the domain. And that would mean direct substitution. And that's just 0. But we're not going to be able to do this from the left because it's going through numbers that are not part of the domain. Oh my God. Now here we have these piecewise functions. I'll tell you what. Now I know that Symbolab is capable of graphing these, but I've never in my life been able to find where you actually enter that information. So what I usually do is to get around it, I just go right to Google. And there is a piecewise functions calculator, but I mean, if you could find it in this menu, in these menus, you let me know because I've never found it. So anyway, here we go. It's 4x minus 3, as long as x is strictly less than 2 and x minus 3 squared everywhere else. All right, here we go. Wow, what a mess. So now what is going to happen here is that clearly there is the limit as x approaches 2 is going to be undefined because it's different coming from the left and the right. So here it's coming from the left. And by the way, because it's a piecewise function, that means when you're coming from the left, you're plugging 2 into this upper term here. So this is the interesting part. You notice when we're evaluating this from the left, it's the limit of 4x minus 3. In fact, why don't I copy this on here so we can look at it? So when we evaluate the limit coming from the left, we're going to plug 2 into here. And when we're evaluating it from the right, we'll plug it in here. And you can see clearly they're different from each other. So the limit of this function as x approaches 2 does not exist, as we've already seen. But we still have the two one-sided limits. This is a valid one-sided limit. If there's some reason why we need this information, this is a perfectly valid result. It's just that there isn't a single limit for the entire function. In other words, there's no two-sided limit as we approach 2, or for any of the others for that matter. But 2, we know that it does not exist. Okay, there's a discontinuity here where the function jumps directly from here to here. Now, continuity, a function is continuous in a very informal way. Think of a function as being continuous if we can draw the whole thing. This is something I was told in one of my math classes. If you can draw the function without taking your pen off the paper, it is continuous. Okay, in other words, there's no gaps, there's no breaks. So in other words, this function is continuous. This one is not. And sometimes you see something like this going on. Oh, wow, look at that. It's not just a hole, but there's an actual gap there. So in other words, there's different ways a function can be discontinuous. There's only one way to be continuous, but there's different ways of being discontinuous. So here, there's a hole. So f of x is not continuous because f of a is undefined. Doesn't have a value. This one, now this one you can see the function is not continuous. Here, the limit as x goes to a does not exist because it's different coming from the left and coming from the right. Okay, so coming from the left, it's this number. Coming from the right is this number, but they're different from each other, as we've already seen. So the limit at that point does not exist, and that is enough for us to know that the function is discontinuous. Okay, so like I said, there's different ways of being discontinuous. Yes, and so the limit from the left-hand side and the right-hand side are different, meaning that the two-sided limit is undefined. That implies that the function is discontinuous. Now, here's another case. If you notice here, there's a hole, but yet there's this point So that means that f of a is actually this point right here. Aha. Now we haven't seen this case today, have we? No. All the other times we had either a hole or we had a break in the graph, like this one. This is the first time we had the entire function like this where there's a single hole and we still have f of a, but that's not good enough to be continuous because here the technical reason why the function is not continuous is because the limit here, well, it does exist, and in fact it equals this value, it's different than f of a. Oh, so that's another way we can have a discontinuity. Okay, so remember we have seen already several cases where we had a hole, just a hole, and we showed that there's a limit there because it's the same coming from both directions. But here we don't have that because the limit differs from f of a. Okay, so there's three ways we can have a discontinuity. So in order to show that a function is continuous, we must show that the function is defined at x equals a, and you can see that here the limit is f of a. Okay, so that tells us that this is a continuous function. It's not like saying that you can draw it without taking your pen off the paper is let's just say, a very informal way of explaining this. This is the formal way of proving that a function is continuous. All three conditions have to be met. If not, we have one of these three cases. So the concept of continuity will prove to be really important and all throughout calculus. Calc 1, Calc 2, all the calculus courses you'll ever take, continuity is a huge issue, okay? Because a lot of the results that we'll see depend on the function being continuous, okay? When we have discontinuities, then our rules start to break down. Now, here's some nice cases. Polynomials are continuous everywhere. Okay, remember what a polynomial is. It's something like this. Okay, so this is a polynomial. Whether it's second order, it's a quadratic function. If it's third order, it's a cubic function. Polynomials are continuous everywhere. Rational functions are continuous everywhere except where we have division by zero. Okay, and you can go through the steps of proving it. These are the three requirements. So let's say we choose the polynomial, the very simple one, f of x equals x squared. Well, no matter what a we choose, let's say this is a right here. Here's f of a. And as x approaches a from the left, the function approaches f of a. As x approaches a from the right, the function approaches f of a. So that guarantees that there is a limit and it also equals f of a. And that's all we need to prove continuity. Wow. Now this one, the rational, remember rational is just a ratio of two functions, two polynomials rather. So this one, whatever it looks like, actually, let's go graph it in, we know that it's going to have a hole at x equals 5. F of x equals um, x plus one over x minus five. And oh God, where's the hole? Oh, it's not a hole, it's an asymptote. Okay. So that means if you look at it carefully, it's continuous except at five itself. Okay. At five, there's a break. In fact, the function itself changes dramatically, but that's the only point where we have a discontinuity. And in fact, you can see f of five is undefined already. It's not continuous. And then the limit as x approaches five from the right. I'm sorry, actually, the limit is different coming from the left and the right. So therefore, this two-sided limit does not exist. And it also doesn't equal f of five because it doesn't exist. So this is clearly this is not a continuous function. Okay. Anyway, so we still have a ways to go here. I think maybe we'll stop right here. We've got a little bit to go in our discussion about limits. And then when this is done, we can dive into derivatives. Okay, really, to me, the most important chapter in the book. But remember, too, we need to finish this because limits are another derivatives, I should say, are defined in terms of limits. So we really have to understand this material very well before we tackle derivatives. So I'll see you all next time.